B, where is it? So Bn of S. Yeah, so this should be, so in general, Bn of S is going to be Bn of delta 1, delta 2, except in this case here, where it has the same Jordan-Holder constituent as this representation, but you have to do something about them.
What's the definition of BNS?
Well, yeah. So that's the definition is this one, except in that case.
Oh, so that's the definition?
Yes, that's the definition. I'm just giving the definition. So except in that case, and
you define it as a non-split extension?
I define it as a non-split extension, yes, and I am just going to write it down. So it's a non-split extension, and so you define a function log L plus to be log L of x if x is not in ZP, and to be 0 if x is in ZP. And now our Bn of S is just going to be well, it's what you do, you start from Bn of delta 1, delta 2. Then you add things which are polynomial p times log L plus, where this you take the polynomial of degree less than W of S minus 1. And then there is an obvious obvious formula to put if you want to have an action of G on this. And so the L which is here, so the log L, I remind you, is just a branch of the logarithm that takes value L at P. And if L is equal to infinity, this is VP. Okay, so you have one special case where the thing that you have here is in fact locally constant, and usually it's not. And you have to mod out by polynomials, so by W of delta 1, W of S minus 1. So anyway, so the statement that you can prove, that was also proved by Rocha and Liu, is that you have an exact sequence like this, Bn of S in all cases goes to pi of S n goes to Bn of delta 2, delta 1. So now you know exactly what the Jordan-Holder constituent of this one are, thanks to thanks to Schneider and Teitelbaum. And so you can try to read on this Jordan-Holder constituent what are going to be the locally algebraic vectors of this representation. Okay. So, so let me remind you some things about the classical local Langlands correspondence. So I have to normalize it. So we start from M, which is going to be a two-dimensional representation of W of the Veildelin group. Veildelin group of QP. So I remind you, it's just a representation of WQP plus some monodromy operator with some some relation between the actions, and to which we can attach via the usual local Langlands correspondence something that I call local Langlands of M. So I want to describe it in more details in the case where this thing is not irreducible as a representation of W of QP. So for this, I need some notation. So if I have a character D from QP star to L star, then by local class field theory, I can also view it as a character from QP to the Veil group of QP to L star. And the formula is just that delta of G is equal to delta of P to the minus degree of G times delta of cyclotomic applied to G. So cyclotomic is in ZP star, okay, and and degree is just the power by which of the Frobenius by which your G acts on the residue field on FP bar. And so now I want to describe explicitly local Lagrange of M in the case where this M is not irreducible as a representation of W of QP. So there are several cases. And you also want, so M, we assume that M is not a twist of the trivial representation of trivial, but is not irreducible. So you have several cases. So M can be the sum of two characters of the Veil group, but delta, so these two characters should not be related in the following way. So delta 1 should be different from delta 2 norm minus 1, or delta 2 norm. In which case, there is only one thing you can do, is to define local Lagrange to be the induced representation from G, the smooth induced representation from the Borel to G of delta 2 tensor delta 1 x minus 1. And you are lucky because here there is no way to distinguish delta 1 and delta 2. And this is exactly the same thing as the smooth induced representation of delta 1 tensor delta 2 x minus 1. So in this case, you actually have an isomorphism. And in our world, you just have extensions between the things that should be isomorphic. So what is more interesting is what happens if M is delta plus delta norm. Then there are two cases. Either n is equal to 0 or n is non-zero. So if n is equal to 0, then local Lagrange of M is not going to be irreducible. It's going to be the smooth induced of delta norm tensor delta norm minus 1. So this one is not irreducible. It is an extension of the trivial representation by the Steinberg, twisted by delta. Okay.
The first one is delta 1 not in that set, right?
What?
The first one is delta 1 not in that set.
Delta 2.
Right, but the delta 1 is not in that.
Delta 1 is not. No, of course, yes. Sorry. So in that case, it's not irreducible. And if n is non-zero, then what you take is just the Steinberg constituent of this thing. So it's delta tensor Steinberg. Okay. And then there is the last case where M is a non-trivial extension of delta by itself. And because I assumed that it was not a twist of the trivial representation, so it cannot be. In that case, you have delta tensor this extension, where you put the periodic valuation here. And then the local Lagrange of M is just going to be some induced So what is it in that case? Yeah, it's just the induced representation smooth of delta tensor delta norm minus 1. Okay, so I mean, in this normalization of the correspondence, you only get infinite dimensional representation, and sometimes you get something which is not irreducible.
This is a definition, right?
This is a definition, yes. But it isn't. Well, why we make this definition? Because of the theorem that I'm going to state now.
So what about the trivial representation?
The trivial representation, I don't know. It never appears in my theory, so. Well, I have to think of what you put for the trivial.
Classical Langlands, in fact, the map factors through semi-simplification of the vein part of the
Yeah, but this is very bad from the p-adic point of view, so you should not do that. I mean,
even on the Bertolini side.
no, you don't want that. You really want this correspondence. Well, I'm going to state the theorem, and so the theorem is the following. So if S so is in this part which I was calling Chris. So if the parameter is crystalline or semi-stable, then what you get is that the pi of S alg is equal to the local Langlands of D of S PST. So I have to explain what I mean by that. With this definition, and if S does not belong to that, then pi of S alg is 0. Okay. So there is one thing I have to explain, is what do I mean by local Langlands of DS PST. So maybe I should go here. Yeah, maybe that's not exactly what I want. Yeah, there is one extra condition, because this does not really mean that the Galois representation attached to it is crystalline or semi-stable. There can be a twist. So you have to add here the condition that delta 1 is locally constant. So this is going to imply that the Galois representation is actually crystalline. If you don't put that, then it's a twist of a crystalline representation. So anyway, so I don't want to keep that. So maybe I write it. So yeah, so I define here a local Langlands correspondence, but you extend it to a local Langlands with Veidolin representation plus a filtration in the following way. So assume that you have a filtration file on M with two different weights, two weights, A bigger than B, A smaller than B. Then what you define local Langlands of M with this filtration to be just local Langlands of M tensor the algebraic representation B minus A. Tensor determinant to the A. And here B minus A minus 1. Okay, and then now I have to explain to you how you get this. And how you compute it, in fact. So, because we have a S, then we have a phi gamma module S, which is an extension of R of delta 2 by R of delta 1. And this extension depends on the choice of L. Okay? And now I remind you that with the condition you put here, you have that S is in S star Chris plus delta 1 locally constant, or locally algebraic, in fact. I could, instead of locally constant here, I could put locally algebraic. That works as well. Means that you can twist by a power of cyclotomic character, in fact. Plus locally algebraic. This is equivalent to the fact that the Galois representation V of S is crystalline. So crystalline means that it becomes crystalline over some abelian extension of QP. And the same thing if you put S in S star ST plus the same condition of delta 1, and this is equivalent to V of S is well, a twist of a semi-stable representation by some character, by some algebraic character. Semi-stable, non-potentially crystalline. So, and what is this D of S PST? Well, D of S PST is defined as D PST of V of S. And in this particular case, it can be computed directly without going to Fontaine's ring Bicris, but just by staying in the realm of phi gamma module. And so there is a formula of Berger that tells you how you do this. So by Berger. So in this particular case, this is going to be the inductive limit, so the union for all n. So what you do is that you take your D of S ring and you tensor it with some ring. So you have to add a log of t, and you have to add 1 over small t, tensor D of S ring. And then you have to take the fixed part by gamma n. So gamma n is just the pre-image in gamma of 1 plus p to the n zp. So this small t is just Fontaine's 2 pi I. So it's log of 1 plus t. So the action of gamma on it is just by multiplication by the cyclotomic character. And then I have to explain to you what is the action of sigma on this one. Well, it's the obvious one. So sigma A of log t is equal to what you think it should be, namely log t plus log of sigma A of t over t. Okay, and this has a meaning now because it has a meaning in R. This is a power series that starts with a constant term which is non-zero A, and so this in fact belongs to R plus. So what kind of object do you get? Well, you get a representation of veil de ligne plus filtration. So the veil de ligne representation is just going to be the following. Okay, so the operator n is just defined by a derivative with respect to log t. And so if you want to have nice normalization, you have to put p over p minus 1 d over d log t. And then on this space, you also have a Frobenius. So the only thing that I have to tell you is, so you have a Frobenius here. So you have phi of t, which is pt, and you have phi of log t, which is log p log t plus log of phi of t over t to the p. And again, this is going to converge. In fact, it is going to converge in E dagger, which is inside R. So you have a phi n, and you also have a residual action of gamma. And then, so I just have to tell you what is the action. So this is the n, and now what is the action of W QP? Well, if you take a G here, then it acts by so phi to the minus degree of G times G bar, where G bar is the image in gamma. Okay, so in that case, you just, I mean, you don't have to extend scalars to actually compute the dPST. It's because everything becomes crystalline over some abelian extension of QP. You don't have to go to Fontaine's ring to define it. Okay, you can stay at the level of R and just add some obvious variables. Okay, so how do you prove that? Well, it's just by inspection, basically. You look at the Jordan-Holder constituent, and you ask yourself which one are locally algebraic. So it's clear which one are locally algebraic. It's the B-alg, which are here. And now you ask yourself which one are going to appear as sub-thing. Okay? And so there is only one case which is interesting. So the interesting case is when V of S is Hodge state, but not Hodge state with distinct Hodge state weight. Hodge state weights, but not the RAM. So this corresponds to the case where W of S is a negative integer. So belongs to Z, but W of S is strictly less than 0. So in that case, what you have, you still have this extension here. So you have this extension, B an of S goes to pi of S an, goes to B alg, B an of delta 2, delta 1, goes to 0. And inside here, you have B alg of delta 2, delta 1, which is a potential locally algebraic component. But what happens is that the extension between this one and this one is non-trivial. And so it does not appear as the locally algebraic vectors of this one. Okay. So, I mean, I find this case interesting because you have something that could be locally algebraic, but it is not. I mean, there is some locally algebraic constituent, but it does not appear as a sub. So it does not appear as a sub. Okay. Okay, that's one case where you can do everything by hand. And now I have to explain to you how you do it in the case where you cannot do everything by hand. Yeah, maybe I should say that for most of the proof, what you use is computation of Jacquet modules of all these representations. That's that's the key ingredient everywhere. Okay, to deal with the general case, what we are going to do is produce a Kirillov model for the representation and a Kirillov model for the locally algebraic vectors. And so I have to recall some things about phi gamma module again. So let's fix some notation. So zeta n is going to be p to the nth root of unity. So it's a compatible system. So it's e to the 2 pi I over p to the n. So Rn is, as usual, the periodic valuation of zeta n minus 1, which is nothing else than 1 over p minus 1 p to the n minus 1. What do I need? Well, let's put Fn. This is going to be Qp of zeta n. F infinity is going to be the union of the Fn. We will have H, which will be the Galois group of Qp bar over F infinity. So this is inside the GQP. So the quotient is just our gamma. Ln is going to be Fn tensor over QPL. So it's a product of field. It's not not a field. And so I remind you that we have defined some subring of the Roba ring. So this one was the thing that converged in the annuli, going from periodic valuation 0, where it does not converge, to periodic valuation Rn. So it converges at epsilon n minus 1. And so you can send it to Ln of t in the following way. So you send f to f of zeta n e to the t over p to the n minus 1. So what is this map? So we call it iota n, this one. But this iota n is nothing else, in fact, that Frobenius applied to minus n. So because what we do, so if you want to apply Frobenius minus n to t, what by definition is going to be 1 plus t to the power p minus n minus 1. So you have to extract a p to the nth root of 1 plus t. And the p to the nth root of 1 plus t that you choose is exactly this one, because what you have is that u to the t is equal to 1 plus t. Okay, by definition, because this small t is log of 1 plus t. Okay, so this thing here is nothing else than a chosen p to the nth root of 1 plus t. Okay. So now, using this construction, you define some new modules. So now you start from a D, which is a phi gamma module. Well, let's say phi gamma et al. Of E. And last time I explained to you that to this one, you can define some module D0Rn, which are inside D rig. So I remind you, if you have a D here, you can descend it down to E dagger. There is a D dagger, and then you can extend it to R by just answering with R. So this would be this one, but this one is built as an inductive limit of things like this. And so this allows you to do the following thing. So you define something which I call D diff n plus to be ln double bracket t tensored over E 0 Rn of D0 Rn. So basically what it is supposed to be, it's just to be the image of this one by phi minus n. And so, and here is just iota n that you use to extend scalar. And so this leaves into the same thing, d diff n, which is the same thing, but where you take the fraction field here, not the fraction field, you invert t, which is, well, let's put it in this way, d diff n plus of 1 over t. And this leaves into something which I call d tilde diff plus, which is, well, the same thing, except that you extend the scalar to b Durham plus h. H is the Galois group over there. Tensor, same thing. And this is inside d tilde diff with same definition. This one has a much better definition if you use the Galois representation attached to D. It's nothing else than b Durham plus tensor V of D fixed by H. So you have a direct definition of this one, which does not make use of phi gamma module, and it's very useful to have this description. And here you would have the same thing, but with b Durham inside. And why do we want to? Yeah, so these boards are not big enough. Okay, so and then you define something which we call d sen n, which is d diff n plus modulo t d diff n plus. And this lives inside d tilde sen, which will be the same thing where you quotient by t. And this tilde sen is just Cp tensor V fixed by H. So that's what appears in sense theory. And now, so this construction allows you to define some the sense operator. So you define an operator nabla to be log of sigma A over log A. So this is an operator which lives in the distribution of on the group gamma. Okay, and log of sigma A just means that you take the power series for the log in sigma a minus 1. And you take some a which is not a root of unity, otherwise you're going to get something which is not defined. So you take any a in zp star, not a root of unity, minus mu of qp. So you get an element which does not depend on A, and it's just the infinitesimal action of your one parameter Lie group Zp star. And so this nabla acts, so it acts on descent n, for example. So it acts it acts linearly on descent n. And in fact, it's just sense operator. So the eigenvalues of these operators are exactly the Hodge-Tate weight in the sense of set. So eigenvalues are Hodge-Tate weights. Now, something important is that it also acts on diff n plus, but now this is not a linear action, it's a connection. So if you look at what this gives on coefficient, so it's a connection. So if you apply nabla to t, you're going to get t. And in fact, what you get is that nabla is t d over t dt. And so it acts on d diff n plus, so it's a connection with respect to this differential operator as a connection. Yes, and so the theorem of Fontaine is the following. So Fontaine says that V is the RAM, so V of D is the RAM, if and only if it also acts on d diff n plus and d diff n, because you just invert t. And so Fontaine says that V is the RAM if and only if this connection is trivial. And nabla is trivial. And in fact, if you look at the kernel of the connection, the horizontal section for the connection, they are exactly bases of d the RAM of V.
So this is on d diff.
It's on d diff n, yes.
What's
Any n. Yeah, so I mean, so you go from d diff n to d diff n plus 1 by just extending scalar from fn to fn plus 1. Okay, yeah, and the last thing I should say is that so this d diff n plus is only interesting if n is big enough so that this d0 Rn is big enough. Okay, so you have to put here. Here you have to put, well, I mean, this definition makes sense all the time, but it is only interesting if n is bigger than the thing I called m of d or m0 of d, something like this. Yeah, so the theorem, yeah, maybe I should put the theorem here, is that in that case, this d diff n allows you to yeah, so what is the theorem? So if n is bigger than m of d, if you extend the scalar to b the RAM, so you can go from b the RAM to ln double bracket t d the RAM d diff n plus. Then what you get is just b the RAM plus, sorry, let's put b the RAM plus everywhere. It's b the RAM plus tensor v of d. So anyway, you have all these modules on which you can do differential computation and things like that. And we are going to use them to describe some Kirillov model of our representation. So this is completely general. It works in any dimension. But we are going to go back to dimension 2. So I'm just telling you what we are going to do. And then we take a break. So we start from D irreducible of rank 2. Then in that case, what you have is that pi of D is isomorphic to this thing D tilde modulo D tilde plus as a representation of the mirabolic, as well, even a Borel. I mean, you can put back the action of the Borel just by putting a central character. And this is going to be the Kirillov model. So I will explain why. And so one of the things that we can read in this Kirillov model is what are locally algebraic vectors for B. Okay, and then it's very difficult to read what are the locally algebraic vectors for G, but already just by looking at what could be a locally algebraic vector for B gives a lot of information. And so the first thing we are going to prove is the following theorem. So we prove it after the break, is that if P alg is non-zero, then D is Hodge state with distinct Hodge state weight. Hodge state weights. So A bigger than B, A smaller than B, and in that case, pi is isomorphic to something which is smooth. Tensor what you want, sim B minus A minus 1, tensor det to the A. Okay, so that's not the theorem that you want. What? Pi alg. Yes, pi alg. So that's not what you want in the end, because you want converse, and the converse is going to be true only for the RAM representation. But just by looking at this, well, that's what you can prove. And in fact, you can prove more. You can prove that this one is irreducible, as I will explain. So let's have a break. 50. So alg has some decomposition like this, but with possibly different weights. So we choose just one component of it. So you choose L and K such that P alg contains something of this type. So contains something which is pi naught tensor sim K plus L minus 1 tensor determinant L, and where this P naught is a smooth representation. What? K. It's K plus L minus 1. No? Yes. Yeah, but yes. It's going to be No, no, wait. Well, I don't know. No, sim k minus 1 there. Voilà. K minus 1. Yes, that's not what I wrote, but it doesn't matter. So anyway, you can twist. So by twist. So you can twist D by the minus L power of cyclotomic character, and this is going to remove that. So twist so that L equals 0. And so what you know is that the central character of pi is omega d, so it's determinant of d times x norm x minus 1. But it is also the central character of the locally algebraic vectors. And so you get that it is something alpha times x to the k minus 1, okay, where alpha is locally constant. So what do you get from this from this equality? So the determinant of D is going to be a character whose Hochstate weight is just the sum of the two Hochstate weight of D. So you get that the sum of the two Hochstate weight is K. So that's the first thing you get from this equality. So now what you do is you take a V in pi naught, and you take it fixed by 1, 1, 0, 1. You can always do that by replacing V by some p to the n 0, 0, 1 V. And then, well, because pi naught is locally constant, then you can choose some n such that V is actually fixed by this element. Now, if you are in sim k minus 1, there is some element, the iOS vector, which satisfies the following properties. So it is fixed by QP star. And it is killed, and E is killed by 1, 1, 0, 1, minus 1 to the k, but not by the smallest power of this operator, but not. So if you think in terms of polynomial, you are on.
You mean fixed up to scale?
No, I mean fixed.
You're fixed by diagonal vector.
Diagonal x, y equals to x. Maybe it's 1, 1, 0, 0.
Well, I should have written down the formulas for sim k minus 1. No, I really mean this one. So
You have a lowest weight vector.
maybe I mean the lowest. I mean,
The lowest weight.
yes.
You want fixed by the one that
Yeah.
you want everything to express in terms of the power.
Yes.
It's fixed by the lower triangular unipolar.
Yes.
Yeah, so it's
Yes.
lowest weight.
Okay, it's a lowest weight vector. It's a, I mean, I want this one, and so it's the lowest weight. Yes. So now you use the fact that your pi of d is isomorphic to d tilde modulo d tilde plus, and so you can choose a z in d tilde, which lifts v tensor E. And so you can try to translate the condition that you put on E and V. And what you get is the following thing. So our V tensor E is killed by this one, but not by this one. So in terms of d tilde, what you get is that t to the power k z belongs in to d tilde plus, but t to the k minus 1. So t, I remind you, corresponds to the action of 1, 1, 0, 1, minus 1. So t to the k z belongs to d tilde plus, but t to the k minus 1 z does not belong to d tilde plus. And then the second condition here, this one, implies that when you that in fact our z is almost fixed by sigma 1 plus p to the n. So sigma 1 plus p to the n minus 1 z belongs to d tilde plus. Okay, because this is the action of this group here. Okay, so now what you do is you choose some m in n such that when you apply phi to the m to t to the kz, and then when you send it into these rings here, d tilde plus, d tilde diff plus, it does not belong to t d tilde diff plus. Okay, so why does this exist? So this is one basic thing in the theory, saying that, so this goes back to, the basic construction of Fontaine, that if you have an element x in A tilde plus, and if so A tilde plus is inside B Durham plus. Okay, if phi m of x is in field 1 of B Durham plus for all n, then this implies that x is divisible by t. By t, and where t in this case would just be identified by Fontaine's element epsilon minus 1. Okay, so you can take something, you can choose an m for which this is true. And so you let, yes?
How is d tilde plus related to
D tilde plus. Well, you see d tilde plus, you can send it to d tilde diff plus. So d tilde plus is related to a tilde plus. Okay, d tilde plus is obtained from a tilde plus by transferring a scalar with v and taking fixed pi by h. Okay, so you can send it by the identity here. Okay, and so you get one embedding of d tilde plus to d tilde diff plus. But I mean, nothing prevents you to apply a power of Frobenius before. And that's what you do all the time, in fact. So you have many possible embedding of A tilde plus into B Durham plus by just composing with powers of Frobenius. Okay, so anyway, you choose one m and you let y be the image of phi to the mz in t minus k d tilde diff plus modulo d tilde diff plus. Okay, if you apply phi m to z, then you get something which is in d tilde diff plus divided by phi m of t, but phi m of t always divide small t. So you get something like this. And what can you say about this image? Well, this y, so it is non-zero because of what we have imposed here. So y is non-zero. And because of this property here, what you get is that sigma 1 plus p to the m y is equal to y. Because, in fact, this commutes with Frobenius, and so you still get this. And what does this imply? This implies, it means that you get one fixed element here in this module. And so this implies that one of the Hodge state weight of this module is going to be 0. So one of state weight of this module, but this module is going to be the same thing as t minus kd is 0. And so it means that one of the Hodge state weights of d is going to be k. So implique one of the state weight of d is k. And so you're done, okay? Because you get that, in fact, k is a second Hodge state weight, and so the first. So you have two Hodge state weights, which are 0 and k, and you prove your statement. Yes?
And if the Hodge tensor, I mean, the criterion for Hodge state is that the Hodge tensor set weights are integers.
What? So Hodge state means that the sen operator has to be diagonalizable, so a semi-simple. But here, because the Hodge state weights are distinct, it's automatically semi-simple. Okay. Yeah, so Hodge state means that the Hodge state weight have to be integers, plus the sen operator has to be semi-simple. Okay, so that's one theorem you can prove by just using purely techniques in Fontaine's rings. Okay, so let me give you another theorem that you can prove in the same line. Something that tells you beforehand that your representation P alg is almost irreducible. So for this, I actually need to construct the Kirillov model. So from now on, we assume that D is Hodge state with Hodge state weight 0 and k. Zero and k bigger than 1. And we want to say something about the locally algebraic vectors. So one thing that you get from this condition is that this module d tilde diff, which is here, so d tilde diff, which is Biederam tensor V fixed by H, well, this has a basis with nice properties. So as a basis E1, E2 with the following property. So So it's a basis of a bidoram fixed by H, okay? So the following properties are as follows. So with, first, if you look at E1 t to the k E2, this is the basis of d diff n plus for all n. D diff n plus over ln double bracket t for all n big enough. And the second thing is that the Galois action is particularly nice. So you have that sigma, so A1 is fixed by gamma. So that will give you one element in D doram of V, in fact. And the second one is almost fixed by gamma, sigma A of E2. So it depends whether you are doram or not. So if you are doram, then it is just going to be E2. So it's a second, so you're going to get a basis of a bidoram if D is doram. And if it is not doram, you get E2 plus a term, and this term is just log A times E1 if D if not. So this is this dichotomy that will explain why in the doram case you have algebraic vectors and why here you don't have algebraic vectors. It's this small log A that appears here that is going to explain the difference. So then you define some submodule. So you define n diff n to be ln of t module generated by E1, E2. So this is inside d diff n. And you define xn to be the quotient of n diff n by d diff n plus. And so this is just a module over ln of t modulo t to the k generated by E2. So it's some kind of rank 1 module over ln of t over t to the k. And you define x infinity to be the union of the xn. And you also define x tilde diff, or x tilde to be n tilde diff modulo d tilde diff plus, where you take the same definition here, but instead of putting ln double bracket t, you take the fixed point of bidoram plus by h here. Okay. So now you take a v in P alg, and I'm going to attach to this v some function, and this function is going to be the function in the Kirillov model attached to this locally algebraic representation. So you take some z in d tilde, which lifts v, as we did in the previous proof. And the previous proof tells you that first, well, what we know is that 1 p to the n 0, 1 minus 1 to the k kills v if n is big enough. And this can be translated to the fact that z belongs, well, phi n of t to the power k z belongs to d tilde plus. Is 0, yes. So you get that your z is not something random. It has already this property. And then there is a second thing which tells you that, well, this vector, because the weights are between 0 and k minus 1, is killed by something like this kind of operator. So I from 0 to k minus 1 of 1 plus p to the n 0, 0, 1 minus 1 plus p to the n to the I. V is 0. Okay, and so this implies same thing for z. So some operator lambda kn, which is just the product I equals 0 to k minus 1 of sigma 1 plus p to the n minus 1 plus p to the n over to the I z, well, lambda n z equals this belongs to d tilde plus. Okay, so you have two a priori conditions on your vector if you want it to be locally algebraic. Okay. So what you do is the following. So you define some function kv of x in zip in qp star. So you just take the image x 0, 0, 1 z modulo d tilde diff plus. So what does it mean exactly? So you can write, because of what we said before, z as y over phi n of t to the k. This x here you can write as p to the I a, where a is in zp star. Okay, and so by definition, this is just so x 0, 0, 1 z. So this is going to be so sigma a of phi n of t, sorry, of phi I of y. So this is an element which is in d tilde plus, okay, divided by, well, the same thing here, sigma a of phi n plus I of t to the k. And this is an element which, well, so you can view it inside Biederam plus, and this divides t to the k in Biederam plus. Okay, and so this function does not depend on the choice of z, because if you modify z, you can only modify it by something in d tilde plus, and something in d tilde plus is going to land here all the time. Okay, so you get a well-defined function there, and in fact, it's so because of what I said, what you get is so this kv of x, in fact, is an element of 1 over t to the k d tilde plus modulo d tilde, sorry, diff, d tilde plus diff. And this contains, by definition, our x infinity. Okay, so this module would be something of dimension of rank 2, and it contains something which is of rank 1, which is this infinity. So now the proposition is the following. So the first thing is that kv has compact support in QP. So this is just because when so if you take an I which is very negative here, what you get is a negative power of Frobenius, and what you are going to get is going to live in to be a unit in Biederam plus, and so it's not going to. So this is because phi n of t is a unit in Biederam plus if n is strictly less than 0. So that's the first thing. The second thing, it has value in x infinity. Values in x infinity. So in something of rank 1. So this x infinity is the thing which I described here. And why is it true? Well, it is because of the second property here. So if you look at the thing in here which are killed by something like that, they have to live in x infinity. So because lambda kn z belongs to d tilde plus. So that's first thing. The second thing is that you really have the property of Kirillov model, meaning that if you look at the function k a b0d of v, and you apply it to x, well, what you get is the central character, omega d of d, and then you get something that is the exponential. So I write it first. So it's 1 plus t to the bx over d. So this plays a role as exponential of 2 pi I bx over d in the usual Kirillov model, and times what you think, namely kv of ax over d. Okay, so this is what tells you that you have a Kirillov model. And the last thing is that it is invariant under the action of gamma, which translates into the following thing. So 3 is that, well, V goes to kV is an injection of P alge. So it is an injection because of the property I recalled before, namely if you have something for which all power of Frobenius are in field 1, then this something has to be divisible by t. So if you apply it to here, you see that if this function here is 0, then it means that here you can remove all the factors one by one, and you get something which is going to be in d tilde plus. So it is an injection of P alge in, well, you take the polynomial function. So RC means relatively compact. So it means that it has compact support in QP. So, but they are defined on QP star with value in this x infinity. But this x infinity is just L infinity of t mod t to the k when you have chosen only 2, fixed by gamma. And what is the action of gamma? So, I mean, fixed by gamma just means that sigma a of kv of x is equal to kv of ax. So you have an action of gamma on polynomial just by multiplying by this, and you also have an action of gamma on the coefficient. Okay, and so you get a Kirillov model, and because you get a Kirillov model, then you can use the theory of Kirillov model to prove the following statement. So one corollary is that, so before having proved anything, yeah, I should say, I mean, this proposition is totally obvious. It's except that you have to know a little bit something about Biederheim plus, but it's just straightforward computation. But the corollary is the following theorem. So this uses the theory of Kirillov model for admissible representation of GL2 of QP, of smooth representation. Tells you that P alg is irreducible, or so, except in one case where it could be, it corresponds to this case here. Okay, or it is of the form sim k minus 1 tensored this induced representation delta tensor delta norm minus 1, where here you have an extension of trivial by Steinberg. Okay, so that's what you get from this thing. So now let me try to explain to you how you prove the theorem that you really want to prove, is that P alg is non-zero if and only if D is Durham with distinct Hochstate weight. Distinct Hochstate weight. Okay, so I'm not going to, so so there are two possible approaches, one that you can find in my book and one that was found by my student. So let me first explain to you how I do things in my book. So the first thing you can try to do is analyze the action of WD on D cross DP star. So I remind you that the only thing which is mysterious in the construction is the action of this this Weil element. So on D rig. And the idea is that you want to try to recapture, so try to recapture the orthogonal of the locally algebraic vectors inside here. So inside here you have a sub thing which is the dual of the locally analytic vectors. I mean, if you twist, okay, and you want to describe in fact the orthogonal inside that of the locally algebraic vectors. So what you do, yeah, so the idea of this approach is that this WD should have a lot to do with functional equations of periodical functions. And so you look at this thing which I already introduced. So it's 1 minus phi d rig psi equals 0, psi equals 1. So it contains the same thing with D, psi equals 1. And I remind you, so which I called C. So, but you prove easily that this is the same thing as the algebra of distribution on gamma tensored C, where C was, I remind you, D 1 minus phi. So this is the heart of D. It's 1 minus phi D psi equals 1. And so the way we proved that there existed some locally analytic vectors was analyzing the action of this WD on this C. Okay. So what we proved was if you take WD of C, you get something which I call C prime. But this C prime is nothing else than the C corresponding to the dual phi gamma module. And so the conclusion is the following. So you look at W of D of Z, and then so these things mean that you use an isomorphism between D and its state dual. And the state dual, because we are in dimension two, sorry, because we are in dimension 2, is just a module twisted by the determinant, and then you have to shift by one by the cyclotomic character. So you get a map, a well-defined map like this, which goes from well, it would go from D rig cross ZP star to D Chesh rig cross ZP star. And so the proofs of the existence of locally analytic vectors tell you the following. It tells you that this induces an isomorphism from C rig to C rig Chesh. So when you see this kind of thing, you really have the impression, and if you use the fact that this C rig is really related to Iwasawa theory, you really have the impression that this should encode some periodic functional equations for periodical function. Okay, and so what you do is the following. So this C here, I remind you, it's basically H1 of GQP with value in lambda tensor V, but it is not completely true. It's the that modulo is torsion submodule. So what you get here, this C rig is going to be same thing as H1 of GQP with value in D of gamma tensor V. And so you get maps. So if you have an element mu here, let's say, so meaning that you have a cocycle with value in distribution on gamma with value in V, okay, you can attach to it some what I call the integral of gamma n of chi minus I mu for all n and all I. And this is going to give you a class in H1 of Fn. So Fn is the extension of Qp where we attach p to the nth root of unity with value in V tensor chi minus I. And in this way, what you get, so you get, if you fix I, you get a compatible system of classes for co-restriction. And this gives you another way of describing this module, in fact. Okay. So because of that, then you are going to define two submodules of this C rig using Bloch-Kato theory. So there is two descriptions. So the working description is the following. So you define n rig, so inside the d rig of 1 over t, to be the set of z such that phi minus n of z is in n rig n for n big enough. Yeah, so n rig maybe has disappeared, or is it still here? Well, it has disappeared. So anyway, I remind you that, so no, it's not n rig, it's n diff n. So this NDiff n was just the module generated by the spatial basis. Well, it would be the basis of the DRAM if you were in the DRAM case. And so you define something which I call CPE and CE. So the first thing is you take 1 minus phi, t to the k n rig, psi equals 1. So that's one definition, CPA. But this is nothing else than the set of mu, or of mu, in viewed in this way, such that when you look at the integral over gamma n of chi to the minus I mu, well, this is in the kernel of the dual exponential map of Bloch-Kato, is in the kernel of X dual. And you want this to be true for all n, and for all I between 0 and k minus 1. And then there is a second module where instead, so here you see you take t. T means that you are looking at the infinitesimal action of the unipotent. And now there is something with the action of the diagonal matrices. So the second object that you want to consider is nabla k, where nabla k is just nabla times nabla minus 1 times nabla minus k minus 1. Okay, so that's the differential operator corresponding to the action of gamma, so to the action of the subgroup ZP star 0, 0, 1, applied to n rig psi equals, 1 minus phi n rig psi equals 1. Psi equals 1. And this one you call CE. And this is the same thing, but instead of being in the kernel of exponential dual, they are in the image of exp, exponential, and same condition here. Okay, so it's very easy to describe the structure of these modules. So you have that C rig mod CE is isomorphic to C rig mod CPE, which is isomorphic to R of gamma mod nabla k. So that's very easy to prove. It's something like Chinese remainder theorem. What is and the main difference between the case of DRAM and the case non-DRAM is that if D is DRAM, then you have that CE is equal to CPE. For the good and simple reason is that in that case, image of exponential is the kernel of exponential dual. So, but if D is not DRAM, then you have that if not, then they are really different, meaning that if you take the sum of the two, then you get the whole thing. And the theorem that you prove is the following, is that in fact WD of CE is equal to C Chech PE, and same thing if you reverse. So WD of CPE is equal to C Chech E. And once you have that, then this allows you to build a sub-module where, so it allows you to build a sub-module of D rig cross ZP star with nice property. And so you're going to yeah. So and by taking the intersection of this module with the dual of locally analytic vectors, you're going to get the dual. And so the main ingredient in this proof, so main ingredient is the following proposition. So I remind you that I have some Iwasawa pairing from CH cross C to lambda. And so you can extend it by extending the scalar to a C rig. And so you have the same thing with CH rig cross C rig to D of gamma. And the main thing is that this pairing here, Iwasawa, so that's true for any figure module, but if you apply this, you get a pairing from C rig to C rig. So xy goes to Iwasawa of WD of x tensor omega d minus 1 y Iwasawa. So this is a pairing on C rig cross C rig, and it's very easy to prove that it is bilinear. But what is more interesting is that it is antisymmetric. So because it is antisymmetric, this allows you to know where, certain line in there are going to go. And that's the main thing. So, the details are long and tedious. So I'm going to not give them to you. And there is another approach by Dospinescu. So yeah. So let me explain how we prove that. So the approach of Dospinescu is to look at the action. So look at the action of the Lie algebra. Of GL2. Well, and in this Lie algebra, you have 4 elements, which I call U minus, which is 0, 1, 0, 0, U plus, which is 0, 1, 0, 0. You have A plus, which is 1, 0, 0, 0. And you have A minus, which is 0, 0, 0, 1. Okay. So if you look at the way these two act, it's easy to describe in terms of phi gamma module. So this one corresponds to multiplication by t. And this one corresponds to our nabla operators. Oh, sorry, this one corresponds to nabla. And then there is one last relation which is obvious, that A plus A minus is given by the central character. So it's just a multiplication by alpha plus beta if alpha and beta are the Hodge-Tate weight. Send Hodge-Tate weight if alpha beta are the Hodge-Tate weight. And in fact, so what I told you before was a way to construct the locally algebraic vector for the action of the Borel. And so it means that basically we have a recipe that gives you things which are going to be killed by some power of u minus and some power, some polynomial in A plus. Okay. And now, sorry, it's this one, A plus, this one. So, and now what is very mysterious is the action of this element. Okay. And so we have to analyze the kernel of this thing on the thing which are already killed on these two things. And what Dospinescu proved is the following thing. The theorem Dospinescu is that, in fact, you have the following relationship in so u minus times e plus, u plus, is given by the action of delta minus alpha beta minus delta on d rig cross P1. Well, maybe I should put A plus here. Sorry. Beta minus A plus. So in fact, this implies that there is some infinitesimal character. So this implies existence of infinitesimal character. So for example, if the Hochstate weight are 0 and k, I think that this, so I'm going to say stupidity, that the Casimir operates by multiplication by k square minus 1 over 2, depending on whether you normalize it. Okay, and when you prove that, then well, this allows you to study the kernel of u minus because you have this relation. So you can study. And so you get a much shorter proof in this way, much shorter. Well, he has not written the details yet, but I mean the check that he sent me was much shorter. On the other hand, if you are interested in trying to recover the classical local Langlands correspondence from this p-adic one, then you will have to analyze the epsilon factors, and I think this is the only way you can do it by looking at that. So, okay, so maybe I stop here. What? It is my last lecture, yes.
Thank you very much.
You're welcome.